The constancy of the speed of light, we've seen in the context of all of the ideas of special relativity, has a dramatic impact on our understanding of time. It also turns out, remarkably, that the constant speed of light has a dramatic effect on space and also on mass. And we're going to talk about both of those, but for now, let's turn to the first one, the implications of the constant speed of light for our understanding of space. So first is, why would we expect motion to affect space? Well, it's pretty straightforward, right? Because speed, as we emphasized, is distance divided by duration, which of course is space divided by time. So if we learn, as we have, that the speed of light is constant, well, we've also learned that time is not constant. So that means that space must in some way compensate for the non-constant aspects of time in order that their ratio stays the same, allowing the speed of light to be unchanged. So in schematic language, in order to ensure that the speed of light is constant, space must adjust itself in tandem with time so that the ratio for light stays fixed. So the picture you should have in mind is something like this. If we consider that time is not constant, therefore space must change too in relation to motion so that the ratio, space over time, is such that the speed of light can remain unchanged. And what we'd like to do is take that rough idea and make it explicit. We'd like to now determine what the effect of motion is on space. How are we going to do that? Well, let's work in the context of a concrete example. Let's imagine that we have a train, and we want to ask ourselves, how would you measure the length of a train? Well, that's a pretty straightforward thing to do when the train is stationary, right? Because if the train is stationary, you take out a tape measure and you measure the length of the train, right? So let's get things going. Let's imagine that that is the situation, and we're going to consider the length of a train from the perspective of somebody on the train. So that will be our fearless train rider, George. From his view, the train is at rest relative to him, so he pulls out his tape measure and he simply stretches it from one end of the train to the other, and that way he measures the length of the train, and let's say he finds that the train is 210 meters long. Good. Okay, that's all perfectly straightforward. Let's now imagine that our second character, Gracie, she is on the platform. So from her view, the train is in motion. So she has to use another approach to measure the length of the train, right? She can't really pull out her tape measure and measure the length of the train because the train's rushing by, right? So that's not a way that she's going to measure the train's length. Instead, she does something more clever. Let's assume that she knows the train's speed. Let's also assume that she has a stopwatch. What she can do is the following. She'll start the stopwatch just as the front of the train is passing her. She will stop the watch as the rear of the train passes her. So she knows how long it took for the train to pass by her. She knows the speed of the train, and she simply multiplies them together. She multiplies velocity times time to get the length of the train, right? So let's see her do that. There she is on the platform. She has her stopwatch handy. The front of the train goes by. Boom, she starts the watch going. When the rear of the train passes her, boom, she stops the watch. She gets the elapsed time, in this case 5.9 seconds. She multiplies it by the known speed of the train in order to get the train's length. That's her approach. Now here is the remarkable fact. The two approaches, George's approach, where he simply used a tape measure, Gracie's approach, where she uses this watch and the known speed of the train, they yield different answers, right? So if you multiply this out just in this particular example, 30 times 5.9, 177 meters. Numbers, I should say, which I've made up just to illustrate the point, which is that Gracie has gotten a shorter length of the train compared to George. Now, at first sight, that is hugely surprising, right? But the question is, does this actually puzzle George? Assuming that George has taken the discussion that we've already had to heart, and he fully knows about time dilation. With the notion of time dilation, does the discrepancy in the length of the train from his perspective and from Gracie's perspective, does it puzzle him? And the answer is no. Because from George's perspective, here's what he says. He says, look, I understand Gracie's approach. She's using length equals speed or velocity times elapsed time. But I also know that Gracie, from my perspective, right? I'm now George. Gracie, from my perspective, is in motion. Clocks in motion tick off time at a slower rate. If a clock is ticking off time at a slower rate, it'll show less elapsed time, and therefore it will, in that multiplication, yield a shorter length. So from that point of view, George understands why it is that Gracie got a shorter length, but the question remains, who is right? Is the length of the train 210 meters, as George says that it is, or is the length of the train 177 meters, as Gracie says that it is? Now, you can probably guess the answer to the question of who is right based on what we have discussed so far. The answer is they are both right. The answer is length itself is a concept that we need to rethink. We normally think about length as the length of an object, but in fact, the length of an object depends on its speed when you measure it. Now, where does that idea really come from? That idea comes from the following fact that we have emphasized repeatedly. Simultaneity is in the eye of the beholder, right? Now, to measure the length of an object, you need to measure its front and its rear simultaneously at the same moment. Now, if two observers have different notions of simultaneity, they will therefore have a different notion of the length of an object. No single result is solely right. No result is wrong. They're all equally good. Now, having said that, just a little bit of language. We generally call the length of an object, when you measure it, when you are at rest relative to the object, as George is in the case of the train, we call that the rest length of the train. We call it the proper length of the train, but that just calls out a particular perspective, the perspective of somebody not moving relative to the object. But fundamentally, you can measure the length of an object when it has any speed relative to you, and you will get a different answer depending upon the speed of the object. So the general conclusion then that we are reaching is that moving objects are shortened along the direction of their motion. And let me stress that it's only along the direction of motion that the object will appear shorter. The height of the object will not change at all. And a little tiny argument can establish that. For instance, if you were to imagine that the train were going into a tunnel, right? And let's say it just barely fits. Now, if it were the case that from one person's perspective, the height of an object, not in the direction of motion, if that were to change, let's say I were to say that the height of objects gets smaller. Well, then from my perspective on the train, the tunnel will be smaller. I won't be able to fit. I should smash into it, right? From the perspective of someone who's on the tunnel, it'll be the train that will be shrunk in that direction, and so it will fit. Now, however weird relativity is, it can't be the case that in one person's perspective, there's a crash of the train into a tunnel, and from another person's perspective, there's not a crash. That would really be a contradiction. That would be a paradox. That can't happen, and therefore we learn that it can't be the case that dimensions that are perpendicular to the direction of motion, they are not changed at all. They stay fixed. And so we describe the shortening of an object along the direction of motion. We call that length contraction, or we call that Lorentz contraction. That is the language that we used, and let's take a look at a simple example of that. So here is a case where we're looking at a New York City taxi cab moving pretty quickly along, and along the direction of motion, the taxi cab is shrunken. It is shorter along that direction than it would be when it is at rest. So let's take a look at a demonstration which will give you a feel for the amount by which an object appears shrunken along its direction of motion when you are looking at it. So this little demonstration here allows you to pick the speed of this taxi cab as it's rushing by you. And again, get a feel for this in your bones. As the speed creeps up, not much of an effect on its length, but when the speed approaches the speed of light, the object gets ever shortened along the direction of motion. Now, you can ask yourself a natural question at this stage, which is, does the object in motion really shrink? And if it does, what's the force that's squeezing on it? Now, that's a natural question, but it's pretty loosely phrased, because the main point that we have come to is that the notion of length itself requires a notion of simultaneity, because again, if you're measuring the length of an object in motion, if you first say measure the back of the object and the object moves and then you measure its front, let's say I'm measuring the length of a fish in a pond, right? If it's swimming along and I first measure its tail and I let the fish swim and then I measure its nose, well, I'll get a different length than I would if I measured the front and the back, the nose and the tail at the same moment. So it's critical in talking about the length of an object to commit to a notion of simultaneity, and that requires choosing a frame of reference, because observers in motion don't agree on what happens at the same moment in time. And because of that, different vantage points differ regarding what happens at the same moment. We come to the conclusion that an object in motion has a length that depends upon its speed, because its speed determines the degree of the lack of simultaneity between two perspectives. So if we ask the question again, do objects in motion shrink? The best answer I can give you is yes and no. It definitely is the case that an object in motion has a length from my perspective that is shorter than when that object is at rest. But it's not as though someone has come in with a vice and crushed the object down. It simply is that the old idea that there's a universal notion of the length of an object needs to be updated. By relativity, the length of an object depends upon its speed when you measure it. And that is a surprising result. The length of an object depends on its speed. Now, give you a couple other little examples of that to have in mind. And both of these examples make use of the idea that we discussed earlier, the relationship between observing something and measuring something. So back then, I described how we're mostly focused upon reality. So we don't really care so much about human perception. We care more about what happened in the world to be responsible for what we see. But sometimes it's kind of fun to look at what we literally would see if some of the effects of relativity were visible to us. And in this example here, we are now going to look at a taxi cab, but done more precisely. So this is how a rushing taxicab would literally look if you could see it rushing by at high speed. Notice that the taxicab appears kind of twisted, right? In the last frames of that little video, we could see the whole back bumper of the taxicab, even though ordinarily, if a taxicab was rushing by us, we wouldn't be able to see the whole bumper. We'd only see the part that was nearest to us. The reason for that is a little bit complicated. It makes use of the fact that when we look at something, we are seeing light from the object. Light takes different amounts of time to reach us from different points on a three-dimensional object because those three-dimensional points are a different distance from our eye. If you take that into account, then that little video gives you a really good sense of what it would be like to literally see an object rushing by near the speed of light. The second example puts us inside the taxicab itself, shows us what it would be like to look out the window of a taxicab that's rushing through a city near the speed of light. And as you can see, the world around you, not only does it have the length contraction that we've described, if you take into account the finite light travel time, the differences from one point to another, you see that space has a kind of warped, distorted, curved look. The world around you seems to be curving in around you when your speed approaches the speed of light. So again, if you could find a taxi that could travel near the speed of light, and if you had really good eyes, so you could actually see the world around you as it was rushing by you at very high speed, that is what you would see. So these are some very strange effects that the constant speed of light has on the nature of space, but they all follow directly from the analysis that we've already done with time. So once you know that time has weird features, you know that space must have weird features too, in order that in tandem they can keep the speed of light constant.